meeting in Hartford next weekend. If anyone's nearby, welcome to join. And then next month, we have CB Wells planned to give a talk on some work that he's been doing for a graphical user interface for a calculus of relations, which in some ways will follow a bit of Rem's talk here on relational mathematics. So we'll get started on the talk today. We'll welcome Rem. I think Rem's talk will be about a vision of relational mathematics that he's calling Deconstructivist Mathematics. All right, take it away, Rem.
Thank you for the introduction. Hi everyone, I'm so excited to be here. I'm Rem. I'm a mathematician. I right now work as a mathematical developer at Simuli. My background is, as I said, in mathematics and mostly in algebra and abstract mathematics, especially category theory and now allegory theory, or the theory of allegories, developed by Peter Frey and Andrzej Szydło. The way in which my research, or rather, well, the way in which compassion and compassionate mathematics enters in my research is because as of now I'm working, as I said, at Simuli. We work in the AGI space, so artificial general intelligence, and compassion means to me that the way we treat emergent intelligent agent should be the same way in which we treat young children that are still developing as person and individuals, or the same way in which we treat non-human animals which still possess some levels of cognition, consciousness, and self-awareness. And also, although this is not exactly the field in which I work on, there are, of course, applications of that even in the context of learning of mathematics, because as we try to understand how the brain works, how consciousness works, we need new mathematical framework, and in those new mathematical frameworks that we are aiming at developing, I see compassion as taking a very, very strong role, especially in the future of education. So what I want to talk about today is the process of formalizing mathematical intuition. So the target for my talk, the target for my research is the idea, the target is that the process of formalizing mathematical intuition can be in and of itself mathematically, intuitively formalized. And now I'll try to elaborate a bit more on that. So when we think about formalizing intuition, I guess there are two ways in which this can be approached. So there is a more narrow vision, or that I feel I can label as narrow, and is that idea of formalizing intuition in the sense of adapting the informed guessing that comes out of like researcher or even student or even people outside of like academic circle or industry, but adapting them to what are already prescribed frameworks that are deemed as rigorous by the mathematical community, again, mathematical community at large, so taking account academia, industry, and amateurs and all of that. But we still think in the sense of, yeah, allowing more people to express their idea and then see where they fit into some already pre-existing framework. But what I believe is the more general vision, so what I strive for, what I look for, is actually transcending the current standard of mathematical rigor and adopting frameworks that are more flexible and comprehensive. And this has always been done, perhaps less openly, because if we think about it, the standards of rigor that we have now are clearly not the standards that we had like 100 years ago before the crisis of foundation. And those standards are not the standards with what the Greeks, okay, described geometry, or populations before them first try to introduce mathematical concept into our world. So mathematical rigor is something that is always evolving, pretty much at the same pace as mathematics itself is evolving. And I think that, again, if we are interested into machines and computers that try to approach the level of intelligence and consciousness that we humans possess, or other non-human animal possess, then we don't just need new math in the sense of developing more complicated math from already existing materials, but we really need a new way to approach mathematical rigor. So I just finished my PhD. Last week I had my defense, and the title of my PhD thesis was Analogies, Metaphors, Allegories, Categorical Architecture of General Intelligence, which I admit is a bit of a pretentious title. But since this talk is mainly building from what I learned during my PhD, these three core ideas that I'm taking from literature, from arts, are those of analogies, metaphors, and allegories. So why do we use them in our spoken language? Why do we use them when we like to tell stories? Well, their uses is quite simple. Like, an analogy is a functional comparison, and I believe most people who are familiar with category theory or are familiar with functional programming languages already knows that you can basically compute formal analogies with category theory with functional languages. What is maybe a bit more speculative on my end is that metaphors, which offer the symbolic abstraction part of language, are also modeled by category construction, and we will see, or at least I will hint at some direction in which one can see this happening. And lastly, there is the concept of allegories, which were first introduced into the mathematical realm, as I mentioned in the beginning, by Peter Fried and Andre Shadow. Now, what sort of conceptual understanding is offered by those figure of speech? Well, for analogies is a very elementary idea, and is that of making proportion, making measurements between entities, again through a functional comparison. A metaphor builds upon analogies by what is essentially a comprehension scheme. So I'm taking this expression from formal logic and axiomatic set theory. Now, an allegory is more complicated narrative that uses metaphors and analogies and composes them into a more complicated way to explain some sort of underlying idea or message. And the key component that I like to emphasize about allegories is a sort of dualization properties, which again is quite natural and internal to the language of category theory itself. So, speaking concretely about categories, a concrete categories is a collection of structure sets. So, if we allow ourselves to assume that set theory exists and makes sense and is a good foundation for mathematics, we can start to look at structure sets, so like monoids, groups, semigroups, rings, or whatever. And between all the functions that we can define between them, we single out the ones that actually preserve the structure. And this gives us a very general idea of space in which essentially algebraic theories can live. And those spaces are indeed concrete categories. Now, this process of abstractions into different layers is depicted here in this figure that I've taken from an article called A Functional Architecture Approach to Nervous System, written by Andrew Coward, which is a colleague of mine at Simuli. Well, this is quite sort of a reductive introduction to his work, but so his idea is to formalize and draw comparison, formalize analogies and draw comparisons between how the human brain works or the animal brain works and digital computers. And something similar is done like all the time in computer science circles. Most computer scientists, especially people in the AI space, AGI space, like to reduce the idea of the brain to that of a computer. This can either go into, like the very general sense of, well, everything that is happening is just computation. Like maybe the universe is just like a big computer, but this to me sounds vague enough that it's not informative at all. If we try to look at like the concrete examples of the digital computers that we have built, like the tablet from which I'm giving this presentation, then there is at the most practical level, there is basically nothing to do with like the human brain. They are completely different, mostly because everything in a computer is discretized and perfectly copyable, while in the human brain, this is absolutely not the case. It's a stochastic system for like most of it. But if we abstract from, like, let's say, the hardware level, okay, and we only care about functionalities, which is precisely what we do in functional language, such as category theory, then we can draw like some very useful comparisons between how we organize and structure the inner working of a computer and how evolution organize and structure the inner workings of our brains. And it goes back to Laver, the idea that categorical semantics historically afforded for the first time a third level of abstraction in mathematical thinking. He argued the idea of the category of all categories as a valid foundation for mathematics, and foundation in a sense that is at this point quite different from what people from the set theory community think of as foundation. So this image is also taken from the same paper. And although here we are talking about, like, again, computer components and hardware components, I believe that there is a very strong similarity, or maybe you would say like an analogy, with how we organize and describe and study mathematical structure. So those three layers of abstraction starts with the most basic one, which is pure computation. That is, we only care about quantities, okay? It's the mathematical of counting and rearranging sequences. It's the mathematics of combinatorics and finite structure. Then we can go to a higher level and abstract the components of our mathematical structure and only care about the concept that they represent. So we go into the realm of abstract mathematics. And beyond of that, there is what people used to call as like half a joke, and it's still in use sometimes even today, generalized abstract nonsense, that is reasoning about how we reason about this mathematical concept. And even this can be put in an analogy with how topology was formally, how topology was formalized in order to abstract from the concept of distance. What is a topology? Well, it is a collections of an element from a ground space that satisfies some specific axioms, okay? So when we study topology, when we study relations between topological spaces, we arrive at this three-layer constructions of speaking of collections of collections of collections. And these last layer of collections are not even atomized concept, but they are sets. So they are assumed to be collections of atomic entities. So this three-layer structure could actually be extended, and indeed we will arrive by the end of this presentation at higher level of abstraction with higher category theory. Indeed, in its inception, in its early days, category theory was mainly inspired and developed as a way to generalize construction from algebraic topology. This is what led Alexander Grothendieck to develop the concept of topos in order to realize this analogy with how topological spaces generalize the concept of distance. So now, during my research, I focused myself on the cognitive process of separation. So in our mind, we are constantly trying to separate and discern concepts and patterns between one another, and placing boundaries between them in order to make sense of like the underlying reality that we are all experiencing, or that we suppose we are all experiencing at the same time. And here I draw some, I list some example of those dichotomies, which comes from various fields of science, starting from the foundation of mathematics itself. The dichotomies between axiomatic versus structural foundations. And as I already mentioned a couple times during this first slide, there are two main ways to think about the foundation of mathematics. One is the axiomatic set theoretical formal logic foundation that was mainly developed, or like first developed during the crisis of foundation, so like pretty much 100 years ago. And then there is the structural functional way of founding mathematics, that is the one provided by category theory, with again the idea that I recalled from Laver of the category of all categories as a foundation for all of mathematics. This is reflected quite in a one-on-one fashion in the theory of programming languages, okay, in which we can discern imperative scripting programming languages such as Python versus functional programming languages such as, for example, Haskell, which was invented by Gary Haskell. If we go one step further and we think in terms of AI and AGI, that is artificial general intelligence, there are even there two main approaches. Well, actually three, but the third one, which is what we do at Simuli, the hypercomputing approach, is only recently starting to see the attraction comparable to the other two, because indeed hypercomputing is a way to resolve this apparent dichotomy between the symbolic and the connectionist. The symbolic are systems, intelligence system based on rules, formal rules derived from common knowledge synthesis, while the connectionists are the folks that are mainly popular right now. So deep neural network, transformers architecture, and other related machine learning, deep learning constructions, in which we do not have atomized formal structured information, but the system actually learns from experience through feedback loops and makes up its own internal representation of the universe. Was there anyone trying to speak? Sorry.
I think that was just the microphone, but Rem, maybe we should open it up for a bit of discussion and see if anyone does have a question about this slide. Or do you want to say a few more words just about the last couple parts of this table?
Oh yeah, let me just finish like the last four, and then I
Yeah,
would
great.
be
Okay.
very happy if someone may suggest some other apparent dichotomies. So going even further in the study of intelligence, so studying like real intelligence being as humans and non-human animals, there is this quite hotly debated topic of nature versus nurture. So the idea that whatever behavior we develop during our lifetime is all prescribed by our genomics, or is it something that we learn from the environment in which we grow up? Going into some maybe more like philosophical speculations, there is an apparent dichotomy between objects and subjects. And this only recently, and I'm not a philosopher, so like, sorry if what I say may sound a bit sloppy, but just recently, some contemporary thinkers started to question the fact that objects are actually capable of possessing agency, in the sense that we as humans act and take our decisions, sometimes even life decisions, based on the interest that we have for the preservation or construction of certain objects. And so one could argue that it is indeed the object that it's influencing, its creators, and not the other way around. And if we go one step even further into the realm of metaphysics, there is the like 1,000-year-old problem of mind versus body. Like where is consciousness stored? Is it in the brain? Is it in the hardware that we run? Or is there something more about it? And the last dichotomy, which perhaps is the most is the most apparent of those, is the one in which it is harder to draw a separation line between the two, is the difference between theory and fiction. What I mean by that, and what William Burroughs meant by that, is roughly this idea that fiction, so like medias and stories that we tell, are by definition something that's not real. It's just a representation of reality. It's not something tangible. It exists in our mind when we experience, when we consume the media. But at the same time, this is something that kind of makes us all agree that there is an objective reality, that there is like a real world around us, because we know that there are stories that we tell that are not part of that reality. They are separated from that. But those stories actually tells, sometimes they tell a lot about what goes on into the mind of the authors, or into the mind of the people that read them or sees them. And even then, the actions and decisions that people make are influenced by the sort of media that they consume. So fiction is not real by basically definition. What I'm saying is a tautology that may sound like too trivial to be said out loud, but at the same time, it affects our real and contingent world. So yeah, now I would like to know if there is like anyone that has some other dichotomies to propose that may be related to the list that I'm compiling here.
Yeah, attendees, feel free to suggest some.
Yeah.
I'll give a bit of a pause, and then I'll maybe ask a follow-up question.
Well, Rem, let me ask this. An often experienced dichotomy in the practice of mathematics, but also more broadly, is that between formalism and intuition. Where would you see that fit?
Oh yeah, that's pretty much like the overall theme of the talk, right? Yeah, there is there is this like, or at least it is perceived by people that work as mathematicians, or people that study mathematics, that on one hand you have like the formal stuff, the mathematics that has been approved by the consensus of the community, and that is the one that works and actually describes our reality to the best of our knowledge. And then intuition is something less highly regarded. It is regarded as something that is, of course, like useful for the development of mathematics, but is somehow like second to it. Like the point is still, as I was saying in the beginning, to in the narrow vision that I explained in the beginning, the one that I'm not adhering to right here, that intuition are sort of like pre-state of mathematical knowledge. They are just like something that can help us, get some insights on what the next theory will look like, but they are not the real thing. The real thing is what you get after you have submitted those intuitions to the constraints and of the frameworks that are widely accepted by the mathematical community.
What I had in mind was to parallel that dichotomy with a dichotomy between what I will sort of loosely call language versus meaning, where language plays the role of some sort of formal system, like a syntax, a grammar, symbolic manipulation, whatever you want, it could be natural language for that matter. It doesn't have to be formal in the mathematical sense, but it satisfies certain forms, certain rules, versus the possibility of there being a different space where meaning resides, where, similar, analogous to intuition, right? And what I have in mind is the functional distinction between what we say and instances where we have the feeling that we're not saying exactly what we mean, but perhaps we can still engender what we mean in the mind of our listener. So there's some sort of compositionality issue there. I wonder where if you see this fitting in
yeah,
the
no, okay,
framework.
now it's clear what you asked. Yeah, no, this is also a very deep problem, and you can see why if you think about the fact that now everyone is crazy about large language models, right? Those models have no internal idea of meaning. They don't know what they are processing. They only care about correlations between words, or not even words, token, but that's beside the point, even if they were words. So yeah, that's also another apparent dichotomy. Why is it apparent? Because of course we develop language to express ideas, even though we are fully aware that language is in many cases it's like too little to express the full human experience. This is why we have also arts, music, visual arts, and digital arts, and whatever, because sometimes you cannot really just infer meaning or ideas or messages just through language, or even on, like the other way around. You can use language in, for example, deceptful ways in order to push forwards another sort of meaning, and then have like the true meaning like sort of hidden behind.
I have a question, Ram, although maybe it's more of a another chance for you to elaborate on some of your prior ideas here. So, your earlier slide about analogy, metaphor, and allegory. One thing that struck me about that, right, is that um, those tend not to be, well, two things. At least with analogy and metaphor, it tends to break down these dichotomies. We're trying to draw some continuity between these. And then it was, so my first question was why allegory has this dualization to it. But now I'm wondering, with these apparent dichotomies, if you see some connection where there's maybe an importance to dualizing. So you kind of want to get rid of them in one way, but in another way, maybe there's something kind of important about dualization in this. Um,
Yeah,
do you have an opinion about that? Maybe about how dualization arises, or maybe how you see, because you use the word dualization here, and I'm curious how that comes back to the allegory.
yeah. No, you're perfectly right. Yeah, so the point about dichotomies and dualization is that I see this as a sort of like necessary procedure. As I said when I started like explaining this slide, is that like our brain constantly try to separate concepts and try to draw boundaries between them. But like after you've done that, you have to sort of like recompose stuff back together to see if your model of the world was coherent in some way. And what may happen sometimes, and I think I will talk about it in a couple slides, is that we try to only focus on one side of the coin, right? And we do that to the point that we don't even realize there is an alternative. We don't even realize we're one side of a dichotomy, and again, like an apparent dichotomy, because I believe all of these can then be like resynthesized together. But even if that were the case, we fail to realize that to most concepts we have a dual concept that arise basically for free when we define the concept in the first place. And for everyone that knows category theory, that probably rings a bell as like the property that every category comes equipped or comes together in pair with its opposite category. And this is something that I think I will talk in 3 or 4 slides. What was that? What you were?
Yeah. That's, I like that. Thanks.
Okay. So like, if okay,
I have a question real quick about this slide right here.
Uh-huh.
This is Matt Insall here. So the last line says reality theory versus fiction. Could you, if you haven't already, I'm sorry, I came in a couple minutes late or so. Can you kind of explain a little bit about why that would be considered a dichotomy? It seems to me that some theories include some fiction, and some fiction it fails to be theoretical.
Yes.
So I would think that fiction would be versus reality or something like that, rather than theory versus fiction. Thank you.
Okay. Yeah. So okay. Now, thank you for your question as well. As I explained before, the terms come from the work of William Burroughs. He came up with the idea of theory fiction. So this is where I'm taking the terminology. I agree with you that the real dichotomy is between reality and fiction. So here, theory is mostly like a way of saying like the objective reality, or at least like the part of objective reality that we take for granted exists, unless you are one of those very cynical philosophers who thinks that like nothing real actually exists. But if you take for granted that at least some like objective experience is possible in this universe, I also mentioned the fact that this last one is probably the dichotomy that is most just apparent. It's just an apparent one, in the sense that it's really hard sometimes, and especially for some people, to draw a line between what is reality, what is like experienceable objective stuff that can happen, and what is fictional, okay, especially in this day and age. But the point is that what I explained before comes from the idea that fiction is a tool that humans use to sort of sanity check the fact that some stuff happens and some stuff doesn't. Some stuff just happens in our mind. And what happens in our mind tells us about what happens in the real world, and what happens in the real world influences what happens in our mind, like in our interior world. And starting from the work of Burroughs, so the last like few lines of these slides talk about a concept developed by the CCRU, which is the Cybernetic Culture Resource Unit, and is the concept of hyperstation. What is a hyperstation, which is the hyper version of a superstition? It is a self-reinforcing emergent mimetic concept that persists in the collective unconscious to the point of affecting reality. So there are some fictions that influences humanity so much to the point that you cannot even label them as entirely fictional. And again, a quite silly example is the tablet that I'm using right now to give this presentation, which tablet, the touchscreen technology and touchscreen digital computers were a thing in sci-fi media for decades before we actually invented them. And it's really weird to now look back, for example, some like Star Trek episodes from the 70s and see that they are in some sense basically using an iPad, even though like Apple wasn't even around during those days. The AGI singularity, so the concept of AGI singularity was actually, not first developed, but was one of the first contributors were precisely the CCRU, and they explain the singularity as basically the embodiment of digital hyperstations. So the AGI singularity will happen, not because it is something that right now is already tangible in our universe, but because we want it to happen. And people like me who work in the AGI space, maybe even unconsciously, will work towards the coming of this singularity, maybe sometimes in the future. Some people say that we will reach the singularity in 5 years. I doubt that. Honestly, I'm not that optimistic. But if in the future that happen, then that means that it was, you know, always supposed to happen, and we get to some sort of like circular causality in which the fact that the singularity will exist now triggers its existence in the first place.
Thank you. I have a follow-up question.
Please go.
You had asked earlier that we, I did hear this request, but I didn't get to say it yet. You asked earlier if we had any others in mind besides what's on the slide. And I did think of this one, at least an apparent dichotomy, and I think an actual dichotomy would be the notion of a dichotomy versus a false dichotomy. Could you elaborate on that?
Okay, I wasn't prepared for this. That's a very clever question. Yeah, I like that. I like that a lot. Yeah, I don't know. Do we get into some like liar paradox sort of situation if we ask ourselves if the dichotomy between the actual dichotomies and apparent dichotomies is an apparent dichotomy, or is it an actual dichotomy?
Well, it seems to me you could approach that the same way we deal with Russell's paradox and Liar's paradox, is to limit the class of things that you're applying the notion of a dichotomy to. That, I know that's not quite in the spirit of category of all categories, but it's still, maybe that's the way to approach it if you want to not limit it, is to think of the category of dichotomies as including including various other categories of dichotomies or something like that, so that you've got the category of, or the dichotomies of dichotomies, or category of dichotomies, something like that. I'm not sure, but it just struck me that in discussing dichotomies, and specifically in modern political lingo and the landscape, the notion of and social discussion and discord, the notion of a false dichotomy comes up often enough. In any case, thank you.
Yeah, thank you for your insight. Thank you very, very much for the insight, because I guess it also like links back to the next slide, in which, yeah, I quote the fact that like 100 years ago, almost 100 years ago, during the crisis of foundation, like as you said, like we found out that in order to avoid Russell paradox or similar paradoxes, what you need to do is to restrict the comprehension scheme. So like essentially restrict the universe of discourse over which you are casting the construction of your sub-collections. All the paradoxes that comes out, you know, in this way are basically like a reformulation, sorry, of the liar paradox, which is like thousands of years old at this point. What those, like, why those assertions are paradoxical to us is because they involve their core an incoherent use of circularity. And so what happened, for example, during the crisis of foundation, is that we developed axiomatic system that provide for formal definitions of induction and recursion. And by formal, I mean that they are sound and coherent use of circular calls, which is basically like what we needed to have early software abstractions. Now, in mostly like any sort of reasonable theory, even taking this sort of restriction into account, one can internalize these arguments about circularity and came up with diagonal arguments that express the limitations of a theory. And this ends up in giving sort of Gödel theorems, so Gödel-like meta theorems that pose practical limitation on the abstract framework, but in practice also on computational architectures. And as you also said, those sort of like restriction of the comprehension scheme, those restriction on the use of circularity are not always in the spirit of category theory, or at least they are not in the spirit of category theory as a foundation for mathematics. Instead, what we have in category theory is the microcosm principle, that is this idea that mathematical objects live in categories that carry a generalized form of the properties that characterize them in the first place. So it's sort of like a mathematical way of expressing the idea that like the inner workings of the universe are reflected into everything that inhabits the universe. And going back to what I also said about the fact that sometimes people don't even realize that there are dichotomies, don't even realize that there are two sides from the same coin. Here's a quote from Crops and Seeds, which is the English translation of one very famous writing from Alexander Grothendieck that I'm not going to pronounce because I don't know French. But it says that like most mathematicians constrain themselves to a fixed framework. This framework was given to them, okay, because it was as it was developed during generation and during thousands of years of mathematical traditions. And here there are two words that are in boldface, and they even in Grothendieck's original writing they are underlined. Though that universe is both familiar and also immutable. And the fact that it has to be immutable is something that, in my opinion, goes directly against what should be the spirit of mathematical research, what should be like the spirit of research in general, that is to develop new stuff. But when we actually work with prescribed frameworks, when we work with prescribed guidelines, what happens is that we just tend to, elaborate on that. We just tend to create more of what was already there by simply mimicking what other people did before us. And I'm not saying that this is wrong or that it is like unneeded or that it is in like some way like diminishing, of the practice of doing mathematics. But it's very important for me that we realize that at some point we need to just like step out of our boundaries. We need to get out of our comfort zone, and we need to consider ideas that were first thought to be just intuitions, but they offer some key insight on how mathematics should be developed in the future and future generation of mathematicians. In my view, what happened during the crisis of foundation, and I don't even like to use the term crisis, because what I believe happened is that we have affirmed a new era of creativity. Like if we think about it, non-Euclidean geometries, which were once thought, like originally thought to be just like a mathematical artifact, are now standard tools in physics class. Like you learn that in a bachelor in physics. You learn that our universe is non-Euclidean in like for most of it. Summability theory, which I will also talk briefly more in by the end of this talk, gave rise to the theory of nets and the theory of ultrafilters, and those were like the baby step for the categorical construction of limits and colimits, which are everywhere in mathematics. How one could see axiomatic foundation is that they allow for greater flexibility, because you can simply come up with your own rule of the game. And indeed, we can give game theoretic interpretation of different axiomatic frameworks. Lastly, but in my view, most importantly, we now have diagrammatic languages, which are a new mathematical tool, and not just a mathematical tool in the sense of like math concept, but in the sense of pedagogical tool to explain mathematics to people, to explain mathematics to different sort of students with different sort of strengths and weaknesses. And this is something that just more than like 80 years ago was unthinkable. Before peers, before the development of category theory, this was simply not there. And whenever I used to like teach privately for like a couple times, and most of my students sort of gave me this weird look of like, well, but so does this mean that mathematics is just made up? There is also like maybe another dichotomy: is mathematics an invention or is mathematics a discovery? Either way, do we just make up the rule? And if so, because that's pretty much what we decided to do like 100 years ago, how can we trust what sort of mathematics we should use in our everyday experience? Like, how can we decide that one axiomatic framework is better than another? And I'm not asking that in like a technical sense by using like strongness results or robustness results and stuff like that. I'm asking that at a very pragmatic level. So in our everyday life, what sort of mathematics should we trust? And maybe in this there is the last dichotomy, and I maybe this doesn't fall into the dichotomy between actual and apparent dichotomy. This is what I call the dogmatic dichotomy. And it is the dichotomy between real mathematics, which is the mathematics that models physical phenomena and has been established through centuries by authorities, and that is useful mathematics, versus abstract mathematics, which, as you know, the name suggests, it abstracts into the ideal world. It integrates different exotic perspective, and for that reason, it is labeled as useless. Okay. The CCRU talks about these in their like very colorful way, talking about the one God universe. What is the one God universe? Is this narrative that incorporates all competing fiction into its own story, and it reduces those alternative reality systems by negatively marking them as components of its own mythos. All the reality programs are evil. Okay, they are useless. OGUs works through fictions that repudiate their own status as fiction. So it is a fiction that claims to be reality, and it hides itself behind this dichotomy of being the real deal, while everything else is just like evil stuff. It's manipulative in some sense, and this is the situation that I was referring to when I said that in some situation people don't even realize that there is a dichotomy. Most people, and even mathematical students, don't even realize that you can play by other rules. The mathematics that you learn in calculus, the mathematics that comes from Zermelo-Frankel axiomatization, is not the only sort of mathematics that exists. And not
Ram, I'll just flag for a minute. We have maybe 10 minutes-ish left, so.
Okay, so I think I will skip the technical part and just go straight through the allegorical foundations. Okay. So one exercise that stuck with me from my first year from mathematics was the construction of the rationals starting from the integers. So assume that you have the integers. How do you define proportions, which, as I claimed, are a formalized version of analogies? Well, you simply define pairs of integers, and multiplication is quite easy. Just multiply component-wise. The sum, it's its own ad hoc rule, but whenever you're fine with that, you define you arrive at defining fractions as being congruence classes that are compatible with both of those operations by declaring that the class of the pair AB is congruent to the class CD whenever A times D is equal to C times B. And this can be pictorially represented as a commutative square. So this is where I said in the beginning that category theory allows you to compute formal analogies. Now, if we want to go from analogies to metaphor, what we need is an idea of diagrams. And diagrams can be formally introduced, or at least in one way to do that is given by André Ehresmann, and that is from the idea of partial functors. And partial functors, in my personal view, comes quite naturally in category theory, because in categories the operation of composition is only partially defined. So now that we have analogies and now that we have diagrams, we can introduce, as maybe the last concept for today, the Yoneda perspective. So the Yoneda perspective is this idea that is also central to category theory, and is that the behavior of individuals are described by by the behavior of the other individuals that they relate to. So in standard, starting from the concrete point of view, we can define rel as the concrete category that has for objects sets and for arrows binary relations. But once we have diagrams, we can actually define tables as being cells that are natural transformations. So sorry, I mismanaged some of my time, so I need to skip some technical definitions. But a table is essentially a natural transformation between discrete diagrams. Discrete diagrams are diagrams which only have objects in their image, so they don't involve any non-identity arrow. And what is a relation? Well, a relation is an equivalence class of table according to isomorphism. In order to define isomorphism, one needs to have an idea of transformation between natural transformation. And so we now arrive at what I hinted in the beginning as being the fourth layer of abstraction. So beyond the first three layers that we already mentioned, we have this hierarchy of objects, arrows between them, natural transformation between those arrows, and then finally what I call thread, because there isn't much like standard nomenclature for that, but I like to call them threads between natural transformations. Now, an object in a category is called preterminal whenever there is at most one arrow of which it is target from any other object. When there is specifically one arrow, then we call that object terminal. And terminal and preterminal allows us to define limit and prelimits for diagrams, which are simply the preterminal object of the comma category of the natural transformation between the diagrams. This allows us to finally define product as limits of the table. And in particular, if we start with an empty diagram, we like to call those objects, we like to call them values. So a value, what is a value in a system based on primitive functional semantics? Well, it is just a relation over the empty diagram. While a subobject, which is a concept, a key concept from Topos theory, is the relation over a constant diagram, which is a specific case of discrete diagram which only have one object in the codomain. Okay, so there was another slide about summability theory, which I'm skipping. So to close this up, what are allegories? Well, allegories are to sets and relations what categories are to sets and function. So we can state this intuitive analogy the allegory of all allegories is to the category of relations, as the category of all categories is to the category of set. Indeed, an allegory is a double category, so it is these three-layer constructions with objects, morphism, and transformation between morphism, such that the collections of arrows between different objects are ordered in some way. They possess a categorical version of order, which is labeled being skeletally thin. A category in which every object is preterminal is called thin, while a category in which the idea of isomorphism collapses to equality is called skeletal. So an allegory is a special type of category in which the collection of arrows are themselves categories. They are skeletal thin categories, and they are equipped with a binary product, which, as we have just saw, that just means that we can form limits of tables, in this case, binary tables, that these tables with two objects. And allegories internalize the opposition and the functors, so they internalize the duality principle from category theory, stating that we can swap the source and target decorators of any category without changing anything about the composition scheme, and this leaves us with a brand new category. And lastly, it satisfies the modular law. Now, the modular law, first of all, the term is a bit bizarre because there is another modular law also from lattice-related stuff that's different from this. But this implication in equation number 7 is essentially what we need finally to have a junction, which, if you are already familiar with category theory and higher category theory, we are probably wondering why I didn't mention adjunctions earlier, because adjunctions simply arise everywhere in mathematics, and this was one of the other key points made by Laver when he proposed the category of all categories as a foundation for mathematics. And the modular law, if you try to write down explicitly what an adjunction is, you will realize that it is precisely what you need in order in order to state them formally. Starting from adjunction, one can prove the Yoneda lemma, which I presented it. I only briefly mentioned it as a principle, but once you have developed a rich enough framework, you can actually prove it as a theorem. Indeed, it is usually proven as a theorem, only without all this machinery about foundations behind it. But the Yoneda lemma, which was originally proved as a theorem, now it has become its own full-fledged perspective or principle in the theory of category, and you can recover that. So you can recover its original status as a theorem in this richer context once you have properly introduced adjunction, and this is again doable thanks to from the modular inequality, the modular law of allegories. Adjoint situation, in my view, are my claim is that they are the formalization of this concept of resolving or synthesizing apparent dichotomies. And as a last, I won't elaborate much further on point number 4. I mostly leave it as food for thought. Once you have all this machinery, you can try to implement in your system a formalized version of Plato's cave, of the allegory of Plato's cave. And my claim is that in the context of AI and AGI, that should serve as a way to measure the emergence of consciousness from an intelligent system. And that's pretty much where I was supposing to end my talk. Sorry if I mismanaged some of my time, but for the sake of it, I just skipped the technical stuff. So yeah.
Yeah, thanks, Rem. Yeah, that does bring us to the hour. I'm glad this kind of nice you've circled back to the beginning of the of the talk with analogy, metaphor, and allegory. And so maybe before we open it up to questions, do you want to spend just 2 minutes um, going back to that very beginning part about how you see now this formal foundation of allegories in the kind of mathematical sense, and bring it back to maybe analogy and metaphor and allegory in the sense of the playwright?
Yeah. So basically, we live in a story that our brain is telling itself, right? So the first thing that we do is try to like compare stuff to see if something is equal to something else, something is different to something else, and if it is different, like how much different is it? So we draw comparison, right? And we do that in a very crude way. And the easiest way in which we can convey that sort of information is through analogies, through saying this is to this as something else is to something else. When you have done that process many times, you can start to collect all that information and try to draw a universal construction out of that. You can try to find an object that concurrently abstracts from all those various comparison, and that gets you a metaphor, or in the language of category theory, that will be a limit of some sort of diagrammatic construction, of limiting construction. Once you've done that in one direction, you then realize that you can go back, you can like backpedal and do every step backwards, or sort of in a mirror universe in which the way in which you with whom you compose object is the same. So the compositional properties are unaffected, but what is affected is this form of orientation. So what you once thought was on the left is now on the right, and vice versa. What you thought was the sky is now the earth, and vice versa. And through mirroring between parallel, sort of like parallel universes, you can now build a full-fledged story. You can build an entire narrative which encompass like the different messages and different ideas, and can convey them through a structured procedure. And this is where I believe allegory can serve as a foundation for mathematics, at least in this sense of doing mathematics in a more intuitive and open and integrative, let's say, way than adhering to standard frameworks of rigor.
Thanks, Ren. Let's open it up to further questions.
So I don't want to overly respond, but I do want to ask one quick question about the title. What's the motivation of calling it deconstructivist?
Because it's dual to constructivist, and category theory is the constructivist approach to mathematics.
Oh, I never heard it that way. Okay. If no one else will ask a question, I'd like to ask real quick. Based on what I've thought of as analogy in mathematics for a long time, where would you place the notion of isomorphism in that early table that I had missed before, and you went back over? And thank you to Nathan for asking me to go back over it.
Oh, so you mean, for example, here, okay, the notion of isomorphism.
Yeah, on the right you have on the right you have proportion for an analogy, and I've always called isomorphisms analogies in my classes. They are perfect analogies. That's what I've been telling my students. So I'd like to know, in what sense is proportion playing that role or replacing isomorphism, and why is analogy not isomorphism in your scheme?
I guess because it's I would say that it encompasses isomorphism in the sense that everything that I'm trying to do is let's say takes into account a sort of direction of orientation. Okay, I'm stressing this very much. And with isomorphism is a situation in which you can go back and forth, as you said, in a precise way. That's like a full. So it would be like maybe I would use the term like strong analogy for isomorphism, in the sense that in like, for example, yeah, no, I just have the square. I don't have the triangle diagram, but yeah, okay. No, so like the idea is that with an isomorphism, you go back and forth without caring about the direction, right? While when you first introducing a comparison, you are just by the sake of like the fact that time seems to exist and flow in one direction, one object will come first, and then there is the second, which again makes sounds as a trivial comment, but it's just the way that it is. I like when people say like, oh yeah, you can take like an ordered pair, but can you really write something an order? Like eventually something will be on the left and something on the right, something will be on top, something will be on the bottom, right? In isomorphisms, that orientation becomes meaningless, and I would say that that's the property that specialize isomorphism as I said, as a strong analogy, so like a stronger version of this proportional scheme that I mentioned.
Thank you.
Thank you.
Hey, Rem,
if you get more questions, I'll be silent, but I'll have others if nobody else does.
Rem, I just wanted to inquire about this last point you were making and what Matt was asking. If what you're having in mind with the word proportion might be related to the notion of the sort of logical notion of ratio, in the sense of being essentially expressible one with respect to the other. What I'm thinking is commensurability or something like that, foundations of geometry.
Yeah. No, that's definitely a better, like any of the words that you use are definitely better than proportion for what I had in mind. So really thank you for pointing it out. I may change my slides for future presentations, but yeah, no, that's what I was trying to get at. So again, thank you for bringing it up.
And I have the point I wanted to make, or the question, sort of I want your opinion about this idea. I do see your scheme as an attempt to formalize the going back and forth between kind of composable models of the world that we can then tell stories about the world with, that make sense to us. And in particular, I'm referring back to a conversation I had with David a while back now, that might be relevant here. And I want your opinion about this. This is a conversation having to do with sense making of a proof, and the idea that the distinction between being able to fully follow and be convinced by a proof and be able to replicate every step of a proof, but still lack in some sense, the sense of the proof, the why, the story behind the proof. And also the opposite being a possible case where you kind of have a very strong sense of why a proof is right, but lack the ability to put it in terms of a formal framework. I think those experiences both are part of the, experience of doing mathematics and learning mathematics and so on. And I wonder if your scheme can shed light on that experience.
I believe this is related to the other comment that you make, right, about language and meaning, right? Like I mean, I think that like the end goal of this would be, as you said, to have a model, or at least, well, a sketch of a model of the world that you can implement in an intelligent, a form of intelligent machine, intelligent computer, maybe. So yeah, I would like, this scheme to be sort of, or this sketch, this draft, whatever, to be sort of like, developed in this direction. And again, going back to like your comment about language and meaning, yeah, I think that's, this is something that is now lacking from, for example, from the current LLM based approach to AI. Not even say AGI, because that's not AGI in any capacity. But even if you care about like narrow interpretation of AI, if we want to write or create, maybe more generally, like stories that tell a compelling and introspective vision of our world, I believe like the issues that you mentioned are like, key perspective to look at, when trying to do that.
Yeah, I mean, I have in mind the moment, the sort of the aha moment experience, right? Where something clicks, and it's not syntactic. It's it's of a different feel. It's almost as though something finally commutes, or I don't know, like something in your scheme might be able to show that. In other words, to represent what happens when sense coheres, and there's a fuller story, a higher level story that can be said. But anyway, I'll leave it at that.
Thank you for your comment.
Rem, I have a question about the connection between the modular law and adjunctions that you hinted at the end.
Okay.
So I'm familiar enough with the modular law to know that some people find it a bit weird.
Yeah.
So I was curious if there is this connection to, maybe just elaborate on the connection to
Yeah,
adjunction.
I'm going to
It's
add
not
to that.
obvious
This was
to me
my
when
other
I-
point, but I didn't want to make it now. But since
Yeah.
you did as well, if you could walk us through, for the benefit of the audience, just like exactly how are we to understand this using the terms you've been talking about, like
Okay, so like the point. Okay, so the way in which you can see adjunction coming from the modular law. Yeah, I'll try not to get into like the technical stuff, pretending that's for the sake of the audience and not because I don't fully remember it. But so if you forget for a second about categories, okay, and try to do everything with lattices. Adjunctions reduce to what is called a Galois connection, right, between lattices. Now, if you write down the formulas for a Galois connection, you get to something that is very, very, very similar to the modular law. And by very similar, I think that it should actually be the modular law if you do the computations right. So why do we care about all of this? Because, okay, so here, remember, we finally got to relations after a whole lot of like technical slides that I decided to skip. But a relation is this equivalence class between tables. Okay, so it's an equivalence class between this transformation. Okay, this transformation between diagrams. Now, what happens, for example, in a topos is that you can look at the objects, okay, and look at the sub-objects, which, as I said, are the relation over the constant diagram that has for image or for target, whatever you want to say, the actual object that you're looking at, right? Now, these collections of relations turns out to be not full lattices, like in a general topos, they are not like full lattices, they are only mid semi-lattices, which basically means that they possess this property here. So these three, they possess the first like property of the definition of allegory. Now, when you perform pullback and push out between arrows, or sorry, over diagrams defined by taking arrows from these collections of relations, you can you obtain a Galois connection, right? And as I said, this Galois connection is basically an adjunction between categories when you see the semi-lattices as categories. So like the definition of adjunction collapses to that of Galois connection in the case of lattices. And so again, what happens is that the equation or the law that gives you adjunction reduce to something deducible from the modular law. Maybe earlier I said that you get exactly the modular law. Now you get something that you get basically an identity that if your ambient category, that is your allegory, satisfy the modular law, then you can check that property actually holds. So you have an internal notion of adjunction between these semi-lattices of sub-objects over the objects of your allegory. So this is how I say that adjunction can be like derived from the modular law. And actually, if you go to the NLab page about adjunction, and there is a section in which they say, like, we now spell out all the details. So they go into like basically element-wise definition, right, of adjunction. At some point, you should see that there is this equation, this identity that I'm referring to, that is really close to the modular law. And yeah, by the way, I never said that at any point, but like, of course, the main references for this talk are the talk from Peter Frey on anti-philosophy mathematics, and also his book Categories, Allegories, written with Andres Shedor, on in which they first developed the mathematical theory of allegories. And this connection between the modular law and Galois connection and then adjunction is completely carried out throughout the book.
Great, thanks. I'll suggest that we stop the recording here, and then we can keep discussion going less formally. Is that okay? So I think because Priya's running the YouTube side here, so we'll stop that. We'll stop it here on the Zoom side, and then everyone's willing to stick around for further questions.